Let's extend this example a little bit to strengthen our understanding. Let's say we are now talking about two independent events, which is getting a heads on a coin toss, which of course we know the independent probability of that is a half, and rolling an odd number on a single die, right? So rather than saying rolling just a 2, we are saying rolling an odd number. And of course, a die has the numbers 1 to 6. 3 of them are even and 3 of them are odd. 1, 3, 5 are odd. 2, 4, 6 are even. And therefore, the probability of rolling an odd number on a single die is a half. Okay, so now let's enumerate each of these, all the possibilities. Of course, the possibilities are still the same. When you toss a coin and roll a die, you can get these 12 possibilities. Out of these, how many satisfy the condition of A and B, right? So heads is all here and odd numbers are here, right? So these are the three favorable outcomes for this joint occurrence of both of these events. So the answer, of course, is 3 divided by 12 or 1 by 4, which is what you get just intuitively looking at it. And of course, if you apply the formula, you get the same thing. It's half times half is 1 by 4. Okay, so here all we are doing is just giving you a rationale for why, when you have independent events, why you multiply the probabilities. Just a quick caution. This formula of multiplying the probabilities applies only when the two events are independent. When they're not independent, then this formula does not apply and something else happens. So let's take a look at an example of non-independent events. Okay, so for example, suppose you're in a university setting, then you could think of an event A as, let's say, the gender of a person is female, right? So you pick a random person, and one aspect of the person you could look at is their gender, and that could of course be male or female. And here I've just given you an example of an event A in which the gender of the person is female. Another thing is the major of this chosen person, right? So the major of this chosen person could be, let's say, history or engineering or whatever, and therefore event B might be this event. Okay, so that's really just examples of two different events. Now the question is, are these two events independent or not independent? Okay, let's say a particular university has 1,000 students, of which 500 are female, 500 are male. Okay, so the university is equally divided among males and females, and therefore the probability of female or probability of male is 0.5. Okay, but let's say that there are, out of these 1,000 students, 300 are engineering students, in which there are 200 males and 100 females. Okay, so the probability of a student, randomly picked student, being an engineering student is 0.3 because there are 300 out of 1,000 engineering students. Okay, and what is the probability of a person being, of the selected person being both a male and an engineering major? Okay, so the male engineering majors are 200 out of 1,000, so the probability is. Let's try multiplying the probability of engineering and probability of male, right? So probability of male is 0.5, probability of engineering is 0.3. So if you multiply the two of them, you don't get 0.2, you get 0.15. Okay, the reason is that these two are not independent, right? What do we mean by that? If they are independent, then the occurrence of one event should not affect the probability of occurrence of the other event, but it does, right? Because normally, if you chose a person at random, they can be either male or female with a 0.5 probability. But the moment you know the person is an engineering student, then the probability of male and female has changed. It's become 1/3 and 2/3. It's not 0.5 anymore, right? Or if you choose, let's say, a non-engineering student, then once again, the probability of the person being a male or female is different. Okay, so the event of a person being an engineering student or not, probability affects the probability of the gender of the chosen person, right? If you choose an engineering student, it is much more likely that they are male than female. But if you choose a general student and don't worry about the major, then the probability is equal that they are male or female in this particular situation, right? So in this sense, the two events are not independent, and therefore this formula does not apply. Now, let's take a look at some intuitive understandings of probability. Okay, so in this section, I would just present to you some problems, some puzzles almost, and we will later on discuss these in some depth. Okay, let's say that uh, if you toss a coin, okay, the probability of head and the probability of tail is 0.5. We know that if the coin is not biased. Let's say you've tossed a coin 10 consecutive times, and it just so happened that every one of the occasions it has turned out to be heads. In other words, you've got 10 consecutive heads. Now we ask a question, what is the probability of getting a tail on the 11th try? Right? When you toss the coin an 11th time, what is the probability of getting a tail, given that you've already got 10 consecutive heads? Okay, so that's one thing. Just think about it. I'm not going to discuss the answer right now. Just think about that. Maybe a good thing for you to do would be to write down your answer somewhere so that you can refer to it later. Here's another question. Let's assume that in a family, a child is born, and let's assume that probability that this child that is born is a boy and the probability that the new child is a girl are both equal at 0.5. Okay, let's assume that that is the case. That's very close to reality, but I think in reality there are some small difference. There is a small difference between these two probabilities, but let's assume this. Okay. Now the question is, let's say a particular family has 4 children. Okay, or if you look at all the families that have 4 children, what is the most likely distribution of the children's genders? Right, so you've got 4 children. The probability of a child being a boy or a girl is 0.5. Both are equal. So if you have family, consider all families of 4 children. Would you likely see what is the most likely distribution of children? Is it going to be 0 male, 4 female, 0 female, 4 male, or 1 female, 3 males, 1 male, 3 females, or is it going to be 2, 2, 2? That is, if you consider only the distribution, is it going to be 4, 0, 3, 1, or 2, 2? Those are the only 3 possibilities. Which of them is most likely? So that's another problem. Okay. This problem again says something about, it says Linda is a person who's 31 years old, single, outspoken, and very bright. She majored in philosophy as a student. She was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Okay, which is more probable? Is A, the event that Linda is a bank teller? That is event A. Event B is Linda is a bank teller and is active in the feminist movement. Okay, which of these two outcomes has a higher probability or is more likely? Okay, so once again, like with the previous 2 scenarios, just write down your answer and move on. Okay, now incidentally, this is taken from this book called Thinking Fast and Slow by Daniel Kahneman and Amos Tversky. A very popular book. In fact, these 2 people won the Nobel Prize for economics for this particular, for the book. And this is one of the items in the book. Okay, it's an interesting book. You can pick it up and read it if you are so inclined. So again, write your answer and move on. Final scenario we have is a game called the Monty Hall problem. This was from a famous TV show that used to occur, I think, in the 90s or maybe in the late 80s and early 90s. Okay, and it works like this. Okay, there are 3 closed doors. Okay, this is a TV game show. So you've got a game show host and you've got a participant, and behind the participant or in front of the participant are 3 doors. All the 3 doors are closed. Okay, but the scenario is that one of the doors has a car behind it, and the remaining 2 doors have goats behind them. Okay, so of course all doors are closed. One door has a car behind it. The remaining 2 doors have goats behind them. Okay, and of course the player wants to win the car. And the way the player is going to win the car is by correctly choosing the door behind which the car is. Okay, so if the player correctly chooses the door, the player wins the car. Otherwise, the player has to take home a goat. Okay, and the way the game works is first uh, the player selects a door. Okay, so the initial thing is first step is the player selects a door. So let's say the player selected door 1. In this particular example, I'm assuming the player has selected door 1. Okay, then what the game show host does is the game show host opens one of the other doors and reveals a goat. Okay, so the game show host is always going to open a door to reveal a goat. Okay, now the player has a choice. The player actually originally selected door 1. Okay, the game show host has revealed a goat by opening this door. Now the question is, the player now has a choice of either sticking with door 1 or switching to door 2. Okay, they can stick with door 1 or switch to door 2. And of course, if after that, that's the final choice. If the car is behind whichever door they now chose, they win the car, otherwise they win the goat. Okay, so the question is, what is the best chance for the player to win the car? Should they stick with the original choice of door 1? Should they switch to door 2? Or does it really not matter either way? Whether they stick or switch, they have the same chance of winning the car. Okay, so once again, think about it. Write down your answer. We'll discuss all of these in a later lecture. Okay, so for this particular problem, it's very interesting. If you look at this guy, this person is a person called Paul Erdos, a Hungarian mathematician, and probably one of the most celebrated mathematicians of this century. Okay, in fact, among mathematicians, a parlor game that they all play is to say, what is your Erdos number? Okay, and the way an Erdos number is defined is, if you directly co-authored a paper with Paul Erdos, then your Erdos number is 1. You directly co-authored a paper with Erdos, right? If you co-authored a paper with somebody who co-authored a paper with Erdos, then your Erdos number is 2, and so on and so on, right? So the fact that mathematicians would rate themselves like this indicates how, how prominent a mathematician Paul Erdos was, okay? And even Paul Erdos had a lot of difficulty understanding this particular problem, right? Understanding in the sense of understanding the correct solution to this Monty Hall problem. Okay, so I just want to point out that our intuitions very often fail us when it comes to probability. Okay, I don't know what the reason is that it should be like this, but that's what reality is. Okay, so in a later lecture, we'll talk about all of these problems and clarify what's going on.